Yeah, thanks for the kind introduction. I'm Yuchen. It's really with great honor to present our paper here. And our talk is about hardware-aware calibration protocol for quantum computers. And this is outline for my talk. The physical error rate plays a crucial role in ISCA devices. For example, previous research has highlighted that the relationship between logical error rates of QEC codes and physical error rates, when and only when the physical error rate is below a certain threshold, when the logical error rate decreases exponentially with code distance. As shown in the figure in the right, we conduct a small experiment to see which procedure may create the biggest damage to QEC codes. And not so surprisingly, we can find out that a drifted 2-qubit gate is far more devastating than a drifted single-qubit gate, or even just exclude this 2-qubit gate away from this qubit code patch. And also, this figure is another accepted research at ISCA, so please catch up with Quantum Session 2 if you want to learn more about how we combine QEC and calibration. So let's take a look at how IBM calibrate their 2-qubit gates. I randomly picked the post waveform of 3 different qubit pairs across the IBM Reasoner, a 127-qubit machine under Eagle R3 architecture. It can be found out that most pulses look exactly the same, with same pulse waveform, with the same function, with the same pulse duration, and the only difference is the pulse amplitude, which might not be as big as you might think. So let's take a look at the underlying data here. For these qubits, the frequency varies from 4.73 gigahertz to 5.04 gigahertz, and the detuning ranges from minus 0.08 to 0.17 gigahertz. And considering the units are gigahertz, and these are the parameters that actually matter in the cross-resonance operations, I would say that they are utilizing quite similar pulse waveforms for qubit pairs with distinct properties. This may come with efficiency, and maybe it's easy to management, but of course, they come with inadequate fidelity. So after monitoring IBM Reasoner for more than a month, it can be seen that the median error rate fluctuates around 7 times 10 to the minus third. And of course, we can find out that some calibration schedule from IBM. So basically, IBM performs daily error measurement for all of their qubit pairs, but they do not calibrate them after the error measurement. So every day, they calibrate around 3 qubit pairs. This is only for 2 qubit gates. And they do not calibrate them based on the standard calibration, which means they calibrate all the parameters they use in the waveforms. Actually, their daily calibration only calibrates the angles in their pulse waveforms. And for every few days, they calibrate around 10 qubit pairs. And for every few weeks, they calibrate nearly all the qubit pairs. And this actually can be seen from the trend in the median error rates. You can find certain peaks in the median error rate. That's because they only calibrate a few angles for a few days. And the error rate drops drastically when they calibrate around 10 qubits. And you can see some trough in the error rates. That's when they calibrate nearly all the qubit pairs. And our research mainly focused on improving the fidelity of 2-qubit gates. And here's our protocol. We proposed a calibration protocol with amplified waveform candidates and optimal pulse profiling for all the qubit pairs. Also, we propose parallel calibration to scale up the protocol. And afterwards, we conduct extensive pulse benchmarking. And from gate level, calibration level, device level, all the way up to application level, we try to validate our protocol. So let's take a look at the waveforms. So these are 2 waveforms that we know already that they can be utilized to implement the ECR gates. They are the equal cross-resonance gates. They use equal mechanism to reduce phase and coupling errors, and they are considered easy to calibrate with moderate fidelity. And here we have the direct CR pulse, and it's actually a little bit harder to calibrate with higher fidelity, but the best part of direct CR is that it's only costs around 6% of pulse duration. And here we would like to introduce a novel waveform. So during the cross-resonance interactions, the off-resonant microwave drive may excite the control qubit in the operation. To overcome the unwanted excitations, a term proportional to the derivative of the drag pose is introduced. And we apply this correlative term recursively to target those dominant transition errors. And as shown in the formula, the omega-3 is the initial input waveform. The initial input waveform has to be carefully engineered so that after recursively applying the derivative forms, the start and the ends of waveforms still at a zero. And we conduct some small-scale experiments. They have confirmed that this multi-derivative drag waveform can reach highest fidelity towards coherence limit, which is a theoretical upper bound for those gate fidelity, and compared with eco-stereo, it's only slightly more difficult to calibrate. So there we are. We have all the poses we're going to use in this paper. But also, we would like to add that direct CR pose can only be implemented with multi-derivative part in it. And when conducting real machine experiments, we found that the original direct CR form is extremely hard to calibrate. So in the following discussion, the direct CR is implemented with multi-derivative parts. And the Zhou various waveform can be utilized to realize the same gate. Actually, a trade-off between gate fidelity, calibration cost, and duration exists. So we have to profile each qubit pairs with their own optimal pose waveforms. And here comes with interesting questions. Should we just calibrate all those qubit pairs and then go through all those 3 different pose waveforms and try to find the best for each one? Or maybe we can subsampling some qubit pairs and find the optimal pose waveform for similar qubit pairs, and then we calibrate them. So with a simple calculation, we can find out that if we subsampling and calibration, it could reduce the calibration total runtime at least 1.65 times and higher in reality. And here comes the profiling techniques. The first idea is quite simple. The effective Hamiltonian of cross-resonance interaction is shown in the equation here. And from the equation, we can find out that it seems there are only 3 important parts: the frequency detuning, the coupling strength, and of course, the harmonicity of control qubits. So we project all the qubit pairs into vectors containing those 3 parameters. And we cluster them based on the Birch algorithm, trying to find similar qubit pairs, and we select one from each group to calibrate them and select the optimal pose for the same group. So the clustering results is shown in the figure here, and we can reach an effective trade-off between computational efficiency and calibration accuracy, because the more group we choose, that undoubtedly will lead to higher calibration accuracy. But also shown in the figure, well, for some figures we can show obvious clustering result, but for some figures the clustering is not that obvious. And here comes the topology-oriented method, where previous research has highlighted that a recurrent pattern among unit cells in the heavy hexagon topology, where qubits occupying analogous positions across different unit cells exhibit similar physical characteristics. And we can group those qubit pairs based on their relative position in a heavy hex cell. And compared with brute force clustering, the cluster size is limited to 12. And the classification process not only includes evident qubit characteristics that we know, but also some hidden constraints generated by the hardware topology. And there are 2 constraints that we haven't utilized, and I'm going to show right now. The first constraint is the relationship between frequency detuning and waveform. So from some real machine experiments, we can find out that under a specific detuning range, the multi-derivative drag waveform is nearly impossible to calibrate towards wanted error extent. And so for those qubit pairs, the multi-derivative drag should be eliminated from consideration, and we should directly apply equal correspondence. And the second constraint is the coherence limit of current quantum machines. So for current quantum machines, actually a sequential of around 250 ECR gates can be executed meaningfully. And the actual situation is more severe for those qubits that have a very much shorter decoherence time than other qubit pairs. For example, in current IBM machines, around 20% of qubits, they have T2, which is less than 60 milliseconds. And for those qubit pairs, it's important to not only consider the accuracy of the ECR operation, but also the duration of the ECR pulse. And also, we propose parallel calibration techniques. So the main idea of these parallel calibration techniques is that we divide the calibration target into calibration subgraphs. And in every calibration subgraph, we choose all the single passes, and we require at least a minimum distance of 2 for all edges in the single calibration subgraph. And for the heavy hexagons connectivity map of 127 qubits, the minimum number of calibration graph is limited to 5. And finally, the evaluation part. We conduct evaluation on two real quantum hardwares, including IBM Reasoner and IBM Nazca. And we implement ECR pulses with built-in symbolic functions, and we implement direct seer and multi-derived drug as custom arrays. The error experiment is repeated more than 5 times to get the mean error, which also means that certain drift errors may also occur during that time. So let's take a look at the gate level results. The gate level results here include all the qubit pairs, and we calibrate them with all the 3 waveforms that we proposed. And the core idea here I want to show you is that for brute force clustering, around 89% of qubit pairs can achieve the highest fidelity. And for the topology-oriented representative, around 94% of qubit pairs can achieve the highest fidelity. And for the hardware-oriented policy, around 90% of qubit pairs can achieve the highest fidelity, because the last policy, they prefer to choose pulse which are shorter in duration. And these are some specific results. So in general, I want to show you that the median 2-qubit gate error is reduced to 4.4 times 10 to the minus third, and demonstrating a 1.84 times improvement. Also, the total pulse duration is reduced by a factor of 1.26. And this is the calibration level result. And in calibration level, we just want to see that compared with sequential calibration, how much faster can our parallel calibration scheme achieve? But as I mentioned before, the direct seer and multi-derived drug are achieved with custom arrays. And currently, IBM has poor support for such custom arrays. So for calibration subgraphs containing more than 10 edges, we have to divide them into 10 edges or fewer. And therefore, in reality, we can only achieve a 39 times reduction in total runtime. But in theoretical, we could possibly achieve a 25 times speed up, of course, but this is compared with sequential calibration. And the next I want to show you is the device level results. In the device level, we choose 2 main targets to show, two main metrics to show our result. The first is quantum volume, which captures the best of the quantum machines, the best qubit pairs. And the second is error polarity gate, also known as EPRG, which can capture the average performance of the qubit pairs in this machine. And as a result, the quantum volume is enlarged from 128 to 256, and the EPRG improvement can reach up to 2.3 times. And finally, some application level results. So we choose some application benchmarks from Open Quantum Bench. And the benchmarks include range from 40 to 23 qubits, and with circuit depths from 41 to 700. And the maximum fidelity we can see here are up to 16%. And that's all of my talk, and please check out our code and tutorial. We'll prepare some tutorials to show you how to calibrate those custom pulses. And thank you for your listening. I'm happy to take any questions.